my talk now is going to be about Ceph durability, okay? So it's like, how safe is my data? Um, I, I guess at some point you learn that like, if you're asking yourself a question a lot and you're like, you think everyone else already figured it out or something, it's like, no, nobody's even asked the question yet. So this is one of those kind of questions that I started like trying to answer it and I like kind of like opened my eyes, mind blown. So what this talk is about is like, it's like we're I'm rethinking a little bit durability and availability in Ceph. Okay, in modern Ceph clusters, there's a few things that are changing in the world that we're looking at. I want to like just briefly remind or like explain like what is durability and availability. Like what are these things in a storage cluster, and then go into practice. And like I really do want to warn. Like I know it's the end of the day. At university, I had an engineering law class at 7 o'clock every night, every like once a week. Yeah, like 7 p.m. and that overlapped with the Vancouver Canucks games as well. I never went. Like I just didn't go. Somehow I got I graduated anyway. Anyway, I'm gonna like introduce a new reliability calculator. Maybe we can play with that one while eating fried chicken. Okay, so motivation. And this is why I wish that Steve were here. It's like now that we have, when Ceph was written originally, like disks were a few terabytes, 10 terabytes. Now it's like 20 terabytes is normal, 30 terabytes is normal. Like sounds like those Seagate boxes are doing 100 terabyte boxes. I mean, OSDs. I mean, I won't get too technical into why that's an interesting problem for Ceph, but it is an interesting problem for Ceph. And like our good friend here, Anthony, has like put in some changes into Ceph, prepared some changes, proposed some, and it's like everyone's going, okay, let's just do it. We just like obviously we have to do it, but I'm sitting there and wait a minute, I'm not so sure. And that's what this talk is about. It's like I'm not so sure. Like we're rethinking some of these fundamental internal constants inside Ceph, and they might have an implication that we didn't expect. So this one, what this exact thing is it's this. It's really just it's a one-liner, right? If you boil down to it, it's like changing, actually it's 1 byte change in the whole Ceph source code. It's like changing this thing, which I don't explain what it is, but it's like changing this thing from 100 to 200, okay? Sounds simple, but one does not simply, right? Now, this is all about, so I think like if we're in the storage industry, we've all like played with those like RAID calculators. Steve was talking earlier about this is how you go from 6 nines to 14 nines and all this kind of stuff. Those are all like kind of like familiar concepts that we have. And in the Ceph world, we've done different work to actually estimate that. We had Mark Campy, and then there was a Google Summer of Code project to do the same, and there's a lot of reports on that. But like with where I've worked in my background, like I think about things the complete opposite way from what those works have done. And that's basically what this talk is about, okay? But first, some background. When we talk about storage being reliable or accessible, or we talk about data protection, it's like those are like loosely, vaguely defined terms. The two like concrete objective things in storage is durability and availability, okay? Durability is like, is my data safe? Can I read the exact bytes that I wrote? And availability on the other side is like, is the system up when I need it? And can I read or write like now? And those are also like still kind of like, what does that mean? Okay, flip it. It's like durability means how much data am I gonna lose per year? And how long until the first byte is lost? Like that's what durability means. And availability means like how much downtime am I gonna have per year? That's what those two things mean, okay? Now, here's an example. The Amazon S3 SLA tells you that they have 99.999999999 durability and 99.99 availability of objects in a given year. So like, what does that actually mean? Let's get the hands dirty, do some basic math, okay? That's 11 nines of durability. It means that if you have like a 10 petabyte cluster, you're gonna expect to lose 100 kilobytes a year. Now, those are expected values. If you remember, if you did like statistics type stuff in university, this means maybe you lose it all in once every million years, or maybe you lose 100 kilobytes a year. And you can also translate it into a number of files too, right? This is just like, on the average, if you had that much, each year you'd lose that much. So that's like 1 kilobyte per 100 terabytes lost per year. That's Amazon, that's what they get. And 4 nines of availability, what does that mean? It means you better plan to have an hour of downtime every year with Amazon S3. That's exactly what that means, right? So in Ceph, we have the same concepts, okay? And we have a lot of fancy stuff written by a lot of smart people, much smarter than any of us here. And well, I don't know you all. Maybe, yeah, probably you guys are smarter. But like, it's like mind-blowing smart stuff, right? And it's flexible, and you can do a lot of things with this too. Like all of that durability and availability, you can like adjust. There's a million knobs that you can do, and you can just pick what you want. And I think it's really like this talk, again, somehow all our talks fit together perfectly today. This is like another picture of something that has been shown twice already today. I'm not going to explain all this text because it doesn't really matter, but it's like this picture here is a typical small Ceph cluster. Each one of these red things is a disk, and each one of these colored things is, let's just call it a PG. Who cares what a PG is? Well, let's call it a thing called a PG, okay? And that's the thing, you know, in RAID, it's like you mirror things, or you do RAID 6 or whatever, but it's like, this is what Ceph looks like. It's just like colored things that are just like randomly scattered across the disks. And your files end up in there. And the question with Ceph is like, it's like, if that thing dies, I don't have the cool animation from Donkey Kong or whatever it was, but like, if that one dies, it's like, is my data still available? Is it still durable? And what would be the answer? If I'm telling you that my files are in those colored things, like, is it still available and durable? Yep. The answer is yes. It's like it's available and durable, obviously. Okay, now if that one fails now in that cluster, is it still available and durable? Yeah. Yeah. Yay. Okay, now that one just failed. Yeah. We're still, yeah. Sweet. Okay, now that one just failed. What happens now?
Available, no. Durable, yes.
Yeah, who said that? Yeah, somebody's got it. Yeah, awesome. Now this one. Same. Sweet. This one? Yeah, we just lost data. And the thing that kind of sucks about Ceph, does it suck? I mean, you really don't want to lose, you really don't, this is like, that was all 3 copies of some percentage of your data. And if you're doing, depending on if you're doing CephFS or object storage or block storage, that can have a different implication for those different things. And if it's block storage, it's like basically what you've just done. You've taken like a shotgun and you've like poked holes in every single disk in your cloud. You like poked like a 4 megabyte. There's somewhere now there's like 4 megabytes missing from their attached image. So you just really don't want this to happen, ever. Now, oh, weird. What a weird slide to have now. Okay, so this is like a weird digression, okay? And this is, I stole a slide from the year 2010 from back at CERN, okay? And this slide, it's like I made this slide back then trying to explain to companies that had paid money to CERN to like partner with them in some way, and like, you know, they just want a white paper to get some promotion out of the thing. And what they're donating was just CPU cores. And like, we hadn't even cranked on the accelerator yet. And they're just like, how is it that you're keeping our million CPUs busy? Like, what are you guys even doing? So this is the answer to that one, okay? Do people know what CERN, if I say CERN, like, does anybody not know what I'm talking about before? Okay, too embarrassed to say, but okay, fine. There's 2, so CERN, like in Geneva, you crash particles together, smash them just to find out what's inside, that's it, okay? There's 2 types of particle physicists. So particle physicists are the kind of physicist that tries to understand like what stuff is made out of. Like stuff that's small, subatomic physics, that kind of thing. And there's like 2, like early on when they're formed, they like choose like one path or the other. And they're theorists and they're experimentalists. Theorists basically sit there and they think, they take weird substances, they think, and then they write equations for how they think the world works, the universe works. And experimentalists they like build machines, really complicated machines, to test if reality agrees with what they did. Yeah, so the Large Hadron Collider is this like massive thing at CERN in Geneva that was built to like, with the latest technology and budgets, like, is there a difference? And if there is a difference between when you do those experiments with like the formulas and the equations and like what you see, it's like then you discovered something. Like that's science, that's progress for humanity, okay? Now, all of that, coming back to that, like why are we burning all these millions of CPUs for this thing? It's this thing called Monte Carlo simulations, okay? Does anyone remember Monte Carlo stuff from university, from math class? Yeah, Monte Carlo is like when you're sitting there in calculus class and they're asking, how do you figure out the area underneath a curve? It's like, so Monte Carlo is just like, well, just like start like picking, like shoot dots at it, and if they're under the curve, you count it, and if they're above it, they're not, and you just do that enough times, and you take like the top, the ones that were in it, divided by the ones that were not, and like, voila, you get your answer. So that's what Monte Carlo simulation is. And basically, like this is what they do at CERN. They smash these things together, and then they get like the whole thing. They spend billions of euros and dollars, and they end up with a plot like this. And what this plot is it's like the dotted line thing is like what the theorists, like what the theory until that time expected, and like the solid line is what you see when you actually do it in real life. And these like colors here is like, that's the standard deviation. It's like how far away it is. The more simulations that you do, so you have to simulate the real thing with the equations, and that gives you this dash thing, and that gets like tighter and tighter. It's like it more and more accurate. You like measure it more and more and more and more until it gets like squeeze it down, and then all this gets smaller. And then when you do it in real life, it's like it has to be, that's what this green text at the bottom is. It's like that bump there needs to be like way above those colored lines, and then okay, we got science. Like that's the whole name of the game. And it's like this is like a plug for scientists. It's like you can trust scientists, okay, because they don't claim that they've discovered something until they're like really, really, really sure. And in this case, it's a discovery if it's 5 sigma. So it needs to be like 5 of those above, and then boom, it's done. And to like, okay, still that's an abstract concept. What does that even mean? It's like this machine that's, I don't remember. I think it's like, is it like 30 miles in circumference, something like that, underground, 100 meters underground. It's the most complex machine in the world. This thing right here is the size of like a building, okay? It's like massive. And they do that, they run it all year, 50 gigabytes per second stored into storage systems, right? And that whole year, like there's approximately like 1 or 2 of those things like found the thing that they were looking for, okay? And so it's like, it takes like, I don't know, what's a number bigger than millions? I don't know, like just billions even, yeah, maybe trillions, I don't know. It just takes like unbelievable amounts of data to do this. Okay, wow. Need a cigarette. I don't even smoke. Okay, so coming back to Ceph, isn't that weird? It's like our good friend here proposed, let's change this number from 100 to 200. And then I thought, well, like if we use all the old ways of calculating reliability, it's like I don't want to write equations to figure out if his answer is like, I just want to try it. Let's just simulate it. So let's be like a Ceph experimentalist. Let's simulate it using Monte Carlo methods. Let's like try to break Ceph. We don't need exact equations. We just need like to, let's be practical. So how do you put the professor jacket on with the padded elbows and everything, right? How does Ceph actually work? I won't go, in the interest of time, I won't go through this too much, but I'll just remind that like there's lots of, Ceph is designed around, it's got a lot of different redundancies and a lot of, one thing I wanted to mention earlier, it's like we talk about different erasure coding schemes, but as if that's maybe the only thing that you can do. But also remember in Ceph, you can do things like put 2 copies over here and 1 here, and in like an erasure code stripe on disks and like this on an NVMe and put the thing, like it's like there's internal stuff that you can do whatever you want. And let's say, okay, I won't go into detail, but I'll just like, as a final exam to see if you're paying attention, like, we have all these disks in Ceph, and we were like failing them, right? So my question is like, it's like, so if I have, normally in Ceph, you have like 3 copies of the data, okay? Does that mean that if 3 disks fail at the same time, I've lost data?
It depends.
It means you might lose data.
Yeah. Exactly. It's like not necessarily. You only lose data if the 3 failed OSDs, like they all had the same PG. If they were all part of that same PG, that's when it happens, right? So like if you have 100 OSDs, like 0 to 99, and then 3, 42, and 71 all fail, it's like, do you lose data? Only if like you look like, this is now like for the Ceph people running the command line, like you have to look for one that had acting with 3, 42, and 71 in any order. It's like if that happened, kaput. Yeah. All the PGs that didn't, all the PGs that didn't have only those 3, then they don't have any data loss. So back like in the early curious days of Ceph, I did something like this already. Like I wrote a little tool, as one does, that just like connects to a cluster, just starts picking random disks and just pretending that they failed and see if it's going to cause data loss. And with that, like, this is what I was saying earlier, like this is a Monte Carlo simulation. It's like, you just like, let's say loop 10,000 times, just pick 10,000 times random disks, numbers, just 3 random numbers, right? And if any PG like was lost, then you record that. So it's like the probability that you're unlucky is like the number of failures with a PG loss divided by your 10,000 or whatever. And that's like, just to like give examples for that, what it really means is like, if you have like 1,000 OSDs, for example, that's like how many ways can you combine those together to have triple failures? It's like 1,000 times 1,000 times 1,000. It's like 1 billion, right? Yeah. And then and then how many of those failures would cause a data loss? It's like, that's just the number of PGs that you have. So if you have only 4,000 PGs, it's like only 4,000 divided by 1 billion of those triple failures cause data loss. Like that thing right there that I just said, like that's the main reason that Ceph is reliable. It's not like there's a lot of other stuff, but the fact that we group objects into PGs and we just have a small number of PGs, that's like the main thing. So then so that's probability that we're unlucky and stuff. The overall like probability of data loss in every cluster, which is then like another way to just say how many 9s that it has. It's just like the probability that you're unlucky times the probability that 3 things fail at the same time. And that's that thing, which is this like probability of the concurrent failures. That's what, that's like the annualized failure rate. That's those things. And everyone guesses it's like 2% per disk. Like any given disk has a 2% chance of failing, something like that. But in real life, we know that those numbers are just like made up, right? The reality is that if that disk failed, okay, like probably like the ones that were in the same server are also failing because maybe it was actually the server that failed, or maybe all those ones with the same firmware bug like everywhere fails. Like it's like the real numbers really vary quite a lot. So it's like it's not even interesting or like useful to get this real probability or calculate the real names. It's like impossible. What's mostly useful is to just compare how it would change if we change what we know about Ceph. We change like the eraser coding profiles, or we change the number of PGs or things like that. So that's what this is all about now. So we don't really care about that thing. We just want to compare. So I would now, if the chicken's not here yet, like bring up this calculator. So I wrote a calculator, and we can like find out, and this is the part that's interesting, and I won't like bore people too much. I'll show the more interesting results. And this is like a work in progress, so I don't want to, let's just get into it. Now, how small is that? Too small? Zoom in a little bit. Let me know. That looks good. Okay, let me get the other side symmetrical somehow. Because we're gonna do that like side-by-side thing. Okay, well, one side's a bit bigger than the other. Whatever, close enough. Okay, so let's see. Okay, so this thing is called like Ceph Sim, okay? And it has like, so it'll simulate. And it's like, let me just do like simulate minus help, just to explain what this thing does. So it lets you tell you like, let's simulate a cluster. It has this many OSDs. The failure domain is whatever. Is it hosts or racks? Whatever. Okay, the default is hosts. We won't really play with that. How many of those things do you have? What's the amount of data on each OSD that you've stored? How many PGs per OSD? What's the size of that pool if it's replicated? Or what's K and M if it was an erasure coded? How many simulations do you want to run? Because this thing actually takes a lot of time to run. I don't have a 1,000,000 core CPU here yet. Next year, maybe. The number of failures that we'll simulate. So this thing is right now by default simulating like triple failures because those are the ones that matter. Random seed and then minus fudge because like that's like when I was saying earlier, like that 2% number, like that's fake. The real numbers are like 1,000 times that or something like that. So we can try different fudge factors to see this. So let's go, just to get an idea what this thing does. So it's running there now. It's simulating a 3x replicated pool on a 100 OSD cluster with 10 hosts, 10 OSDs per host, that means, right? So it calculated we need 4,096 PGs. This is really, if you guys are not Ceph people, like forget it. But this is my special interest, okay? There's an example PG, like this is like how much data is in each PG and how much it's stored and all this stuff, right? And then it simulates the progress bar here that is like in the finest ASCII art I've ever prepared. If there was an X, it means in that like loop, it like found a problem, it crashed a PG, okay? And so in all of those simulations, it's like there were, out of the 10,000 crashes we did, like 260 of them led to data loss. That's how I think about this, okay? So it's like this is a 100 node cluster, triple failures, just random 3 anywhere, like 2.6 of them caused data loss, okay? And then, okay, these parts don't matter that much. Like putting in those just to like have some kind of thing to explain, to map it to our reality, like that's like a 12 nines cluster, assuming 2% failure rate and a correlation factor of 10, right? I'll put like minus fudge, like 1,000, just so you see that like the bottom numbers will get much larger, but everything else will stay the same. And we don't really care about that point. That's not like that interesting. Oh, now it's only 10 nines because the failures are more correlated than we thought. So how do you can't, the real values of this, like we can't guess. So that's the durability. Also, have people heard of mean time to data loss? Like that's actually like a more useful metric in durability. It's like how long until I'm gonna lose data? Because when you lose data, just forget it. Find a new job, right? Okay, so let's do something interesting. Some of the like interesting things that I found with this are like, so we have size 3 over here. Well, we'll just scroll to this one because this is the first one that we want to do. And then over here, I'll just like simulate I'll simulate a, what is it called? Ceph Sim? Simulate. Well, I'll simulate like a 500 OSD cluster just to see like, what does that change? Now the cluster's bigger, but like everything else is the same. Okay, well there's more PGs because we're targeting 100 PGs per OSD still, right? It takes longer to simulate. That's why like you'll find here in this demo today, I'm not gonna be doing the large cluster simulations. I have to reconnect to the supercomputer for that one. I'm still doing 10 hosts. I didn't change that. So it's 50 OSDs per host. And just to get an idea of like what I mean by comparative stuff, we'll let this one finish and then, boom, boom, boom. So only 12, you see? So all things being equal, like a larger cluster is more reliable. When you talk about that side of the overall durability calculation, of course, you have to balance it with this side which we don't know accurately. This side, I know this is hard to like get in to like parse it, right? It's like this side, if I have 100 OSDs or if I have 1,000 OSDs, it's like you're 10 times more likely that you're gonna have triple failures on the larger cluster anyway, because there's just more disks that might fail. So you see, it's like these are not, we can't only look at this one, we have to somehow like multiply these things anyway. That's why like this one, I think we can compare like the mean time to data loss in this one was like that many years. That's a lot of years, right? And in this one, it's that many years, and that's a smaller number. So overall, with the assumptions that I made in this case, like actually the 500 OSD cluster is less reliable, okay, somehow, yeah. Now, that's just getting into that comparative thing. Now I wanted to show like, first let's answer, should we answer Anthony's question first?
Yeah.
Yeah, because we're all getting hungry, right? So num-PGs is 100 on this side. Whoa. How do we call it again? PGs per OSD. Who wrote this thing? We got 100 on this side. I'm gonna like do the same with 200 on this side. Now, when we first like discussed this, we discussed these things in GitHub, as one does, right? When we first discussed it, it was like, oh yeah, maybe the chance of failures is gonna double, but like the size of the PGs will halve. Because if you have more PGs, it's like the amount of data in each one is getting smaller. And so no big difference, right? But that's why I wanted to calculate this and see what it means. Actually, well, this might have been yeah, it shows it perfectly. So the observed incidents like basically doubled, okay? The number of times, so it's true, it's like, because now it's like 200 divided by a million instead of 100 divided by a million. It just doubles. But the amount of data that you lose, it's like it stays the same. We're not losing any more data. However, the mean time to data loss here was like this many billion years, and now it's like half as many billion years. So we're gonna have data loss twice as quickly. That's the problem. So we just now, so then it's like everyone looks at this, yeah, okay, well, I don't know what I'm gonna look like in that many years or what the universe will look like, so who cares, right? So let's see if there are some scenarios where it actually matters, right? This is where it got surprising to me. Let's do size 3 over here with a, let's do a 200 OSD cluster. I wonder if this will show it properly. And here we'll do K, I want to prove my point, 10, and like M, I got to do the math here properly. Let's be stupid and do K18 and M2 just to really exaggerate. Is everything else, did I give any other arguments? No, not really. Oh, failure, why? Because is like, how many OSDs? It has to divide equally. Oh, I didn't write num OSD equals 200 over here. What? I still have to think, how many hosts do I have? Yeah, I need 20, so I have to put like, let's just do this differently. I will not make it so stupidly wide. I'll do it like that. You can't, I mean, for reasons that probably some of you experts in the room already figured out, you can't, like there's it has to fit. The width has to fit. So here we go. Maybe somebody already saw the result more than me. Okay, this is a conventional triple replicated pool, okay, on 200 OSDs, and this is an 8+2 pool on 200 OSD. It's like, I don't know, what's 1,649 divided by 59? It's like much, much less reliable. Because, and we have fewer PGs, so that's even like the opposite of what I said earlier. I said if you have more PGs, you're gonna have like more data losses, but here it's like there's fewer PGs. It's because those, if you're looking in this this is K8M2. We've been through this 4 talks already today. What does all mean? I suspect everyone knows what I'm talking about. It's like if we have 3 disks that fail, we're having data loss in that scenario. So this was the surprising result. I didn't expect it would be so dramatically worse. So we're going, like with all the other assumptions, like we're losing 2 nines just by going to erasure coding. And it even happens for, let's just do our like standard size, like 3, and like, it's like even like 2+2 erasure coding is, well, that's the same one as above, but even 2+2 erasure coding is not as reliable as triple replication. So there were some other, is there anything else? I mean, so you solved the different arguments.
That makes perfect sense too, because if you got a strike
Yeah.
10 devices long
There's more.
Shooting at it with a shotgun.
Exactly.
You're gonna hit more of those
Exactly. Yeah. Yeah, exactly. That's the problem. So, I mean, now after I wrote this and I was like, okay, I'm never doing m equals 2 ever again. It's like you have to do m equals 3 because like triple failures is likely enough that it will happen in the next billion years. But four failing at the same time, that, I mean, with all of the, those theorist equations, it's so much less likely to happen. If we put in like, so just to do the example, and I don't know if I trust this math yet, but like, so let's do the size 3 here, and then let's keep it the same, but we'll say, let's do like 3 plus 3, and we'll say the num failures is 4, so like 4 concurrent failures. So that would still, like, that would cause data loss in the same way, but like how, you see, it's like this number here. So our like, see this mean time to data loss, like, I don't know how many lifetimes of the universe that would be. That's like, so that one I'm not very concerned about as a pragmatist. But the triple failures are the ones that are kind of, they might happen. And like, I think we all know, but like triple failure doesn't mean that it's like, boom, they all fail. It means it fails, and then things start backfilling, which is like higher load on the cluster. Then another one fails, which is like even higher load on the cluster, and then a third one fails. And that happens in real life, yeah.
So you were leading in with larger disk drives, but you're defaulting to 10 terabyte in your.
Yeah, this is like how much data. So that you can just say that that's just a constant factor k. Everything will scale up. The reason why I led in with larger disk drives is because of what I just said there. So these PGs, what it is you take a disk and you just like carve it into placement groups. So in the good old days when we had like only 10 terabyte OSDs, each PG was like 100 gigabytes maximum. And when a disk fails, like that's the thing that you have to backfill. And the beauty of Ceph, I mean, there's other talks you can watch, videos and stuff of this. It's like a disk fails, like everything else in the cluster just goes like, they all do that like in parallel, 100 gigabytes. So recovery time it's parallel recovery. That's the magic of Ceph. It's one of those things, right? But if now, like if you go to 20 terabyte disks and everything else stays the same, now that's 20 terabytes, or 200 gigabytes you have to recover. If the network stayed the same and the disks are still doing their 250 megabytes per second like HDDs do, it's like it takes twice as long to recover. Your danger window doubles. If you've got, I mean, I trust that it very rarely happens, but if you had to recover one of those 100 terabyte or 1 petabyte OSDs that we might have one day, like that's why we say, oh, we just need more PGs. It's easy. Let's just double the number of PGs. Let's just do 1,000 PGs or something. But that's where I'm stepping in and saying, like, it's not so simple. I don't know if we can. We have to think. Yeah.
You actually didn't run with a 24 disk drive in your presentation here, right? You're defaulting to 10 terabyte.
Yeah, sure, but that won't. So we can. I mean, we can write. So we can write the only thing that impacts. I can show you what I mean. Like, so we'll run the size 3 here. And the size, that's just for kind of like display purposes. So is it like TB per OSD? So I'll just put 100. It's like, it doesn't, in the way this calculation is doing, it's the same number of PGs.
Okay, so you increase the number of placement groups. That was the same simulation.
Exactly. The real thing, so yeah, good. No, but very good questions, because you would really, if it was 100 terabyte, you would want to say PGs per OSD is 1,000 to keep everything else equal. And let's do that. Okay, this is where now we need to like call the supercomputer people, because that's not going to work. So I'll just run it with fewer simulations, but I don't know. Can I get 1,000 done in this time? Yeah. But like with this many, I don't know if we'll get meaningful results. Let's see. Yeah, we did. So it was like much more likely because we had 32,000 PGs. It was much more likely. Our mean time to data loss is like much shorter. Yeah. There are some configurations that you can do in this that surprisingly they give you like, they'll give you like, let's construct one, I think like K, let's get one of those like K18 M2, because every manager wants 18 plus 2, don't they? They just love it. So let's say, so that's like 20, we need at least 20 hosts in this one. That's the problem. So I'll just say like, what were my arguments again? They were like, help. So we need like num OSDs. What's the thing is like, it's number of domains. That's like the number of hosts. So we'll just call it like num domains is 20. We'll just say that there's 20 hosts. And this is one of those things where it's like, okay, yeah, in this one, it's like, it's coming down. There are some examples, but like 80, it's like almost all of basically every time you had a triple failure, it caused data loss in this case. Yeah.
Now, Dan, I have to interrupt.
Sure.
In all fairness, the target used to be 200. I just want to move it back for you. But also where I talked about the slow recovery,
Mhm.
when we talk about piece of unlucky, I think there's also the factor, of the media in there.
Oh, of course.
Right?
Yeah.
Where, like TLC as a
Of course.
is going to recover much more quickly than today's 30 terabyte hard drive.
Yeah.
For what I mentioned about the risk
Sure.
of that recovery.
Of course, yeah. And that's this like fudge, this correlation factor. That's what it is. It's like that's embedded in that variable because it's just a question of what's the probability that there's a second failure or third failure in that window. The window might get shorter, but like maybe you've got great technology, but then like there's a sick disk somewhere else that's like almost failing because you didn't scrub because you disabled deep scrub a month ago, and like there's so many things that can happen. That's why I mainly like care about this stuff here, which is like how bad am I? Like how often will those triple failures cause? And then if they happen or not, that's like hard to estimate. Yeah. No, I mean I know. Hey, Anthony, I was like, I think at Ceph Days Switzerland in 2016, I was like, we have like 20 terabyte disks already. Like it's getting larger and larger. What are we gonna do? And yeah, we just don't have a good answer yet. We have to think of a better answer. Yeah.
Isn't progressive failure also just as important? Because Ceph can recover forever, in theory, right? As long as
Yeah.
you have free space.
Sure.
So if you have free space, you recover again, you recover again.
Mhm.
In real life, if you're using, flash storage, right, you have infant mortality, right? Other than that, it's just kind of mismanagement of hardware, if your drives are failing.
Oh yeah.
Right? You either push them too far into the life cycle, not measuring the life cycle. Well, fire that guy.
Yeah, sure. Yeah, there's a lot of operations best practice is one of the huge yeah.
So
Yeah.
but like they fail initially. That's called infant mortality, right? And then they don't fail.
Yep.
And then they fail because they've been around too long.
Yep.
So in this period, you have progressive recovery. So if you have a drive fail, Ceph will recover it. Now you don't have a drive failure. So another failure is not simultaneous.
That's why it's about the overlapping failures, and that's why
All of I mean
profile makes that risk of overlap much bigger. That's necessity.
So you have to do calculations.
yeah, I mean look, this is an ongoing investigation. The important, I mean, in all of those numbers that we saw, I can get some examples to show like it'll fail in 1,000 years, which like still sounds like it's pretty far off, but it's like not acceptable. If you're storing your pension fund data on that storage system, you probably don't want that one, right? So next steps, I want to add like an availability thing to it as well because the downtime is also quite important, and that happens like that. Those numbers will be similar to Amazon's, like an hour, a year, or whatever. Like, and it's quite interesting. I think it's like to really make these things more visible. Like your excellent like website with the configurator, like to make this stuff visible would help people understand. I think more like those choices and make educated decisions. The thing that I just showed, it doesn't talk to real clusters anymore, so I'm going to redo that. And then we're going to bundle it. We have this thing that we call Copilot, like what a creative name, but we have this like CLYSO Copilot for Ceph that this will be like one of the features of that. And we'll put all the posts onto Ceph.io. Yeah, and that's like, so that's the end of that part. I just wanted to like, I always end with like some free cookies or something. There's a lot, like we made this tool for like this, for the thing that I just talked about and like other things like that. Like we have a lot of tools. This thing is like a version of that Copilot thing I was just mentioning. There's a website you can go to, analyzer.clyso.com. And like just like upload, there's like a file you can get out of your Ceph cluster. It's like right there, Ceph report, blah, blah, blah. Upload that file and it'll give you like a report card on how good your cluster is, okay? So if you haven't tried this one yet, I encourage you, you can see how you're doing. This is an example of a pretty bad one. F means bad. I had to explain that to my kids after we lived in Europe and then we came here, they didn't know like everything over there is out of 20. Like, it's like makes sense, right? So this cluster, one high severity bug, they're running version 16.2.10. I mean, if you're running 16.2.10, obviously you're going to get an F. Like everybody knows that, right? So there's lots of things like that. So it'll check different things and it'll give you some advice. And yeah, that's it. Yeah, thanks a lot.